In this video, we're going to look at mass spectrometry, and we're going to focus on this section of mass spectrometry as we've covered other parts of mass spectrometry before. You may remember I showed you how mass spectrometry works when we did isotopes and working out relative atomic masses. And I showed you a PowerPoint animation to illustrate how a mass spectrometer works. If enough people message me on Microsoft Teams to say they need a recap on that, I'll do another video. In that lesson, we looked at M over Z values and what they are, and we looked at relative abundance to work out the relative atomic mass of different isotopes by looking at the mass spectra of elements. In this video, we're going to focus on the spectra of organic compounds and look at what we mean by molecular ion peak, M+1 peak, or the satellite peak. And then we're going to focus mainly on looking at fragment peaks and fragment ions to help us work out what possible structures could form those fragment peaks. You may remember when we did FC3 and looked at the relative atomic masses and relative isotopic mass, we looked at these mass spectra and we used these to work out the relative atomic mass of different elements. At that time, I explained how a mass spectrometer works when a sample of an element is used. We're now going to look at what happens to organic compounds when they put through mass spectrometers. For an organic compound with molecules M going through the mass spectrometer, the molecules are first bombarded by high energy electrons and ionized, and the majority of the time only one electron is knocked out from these molecules. So the molecules bombarded by the high energy electrons will form single positive ions or unipositive ions, and we kick out the electron from that molecule. We always have the high energy electron left over because that's not gained by the molecule. So these molecular ions will then pass into the detector, or sometimes when the molecule passes through the beam of high energy electrons and forms a molecular ion, these ions will fragment. And the reason why they fragment is that these molecular ions are actually radicals because they've lost an electron from the electron cloud of the molecule. These radicals are very unstable, so will break apart and fragment. So sometimes when we write the symbol for the molecular ion, we don't just write the plus sign for the charge of the ion, we also write a dot to show that this is a radical. Just to clarify this diagram bit, this section here represents this section here. So here's the electric plates as shown here. Here's the molecule becoming the molecular ion as shown here. When a molecular ion fragments, it can fragment in different ways. For the A level, you only look at the fragmentation caused by the breaking of one bond within the molecular ion. We also never break double bonds in fragmentation if you want to work at the fragment ions for A level. So for this case here, we could have fragmentation along this bond, which is the same as that one, or along this bond, or this one, which is the same as this, or along here, or along here. So for example, if I fragment the molecular ion here, we can get this fragment ion and the radical that's left over. Don't forget this equation here must balance for charge. So this is a single plus charge ion radical. I'm going to get a single plus charge and a radical. Or fragmenting at the same place, I could get this ion instead and this radical. So you can see there'd be lots of different types of fragments or fragment ions that can form. And those fragment ions form different peaks in the mass spectra. However, the radicals, which are not positively charged, won't be found at the detector. The positively charged ions will be deflected to the detector, and we see peaks of those. We can look at what the mass spectra looks like with those fragment peaks on. So let's look at an example of a mass spectrum for a sample where we know the empirical formula of the compound to be this. So first of all, we look for the most prominent peak with the highest M over Z value, and this will be due to the molecular ion. So this is called the molecular ion peak. So this is caused by the molecule losing one electron as it passes through the beam of high energy electrons in ionization. We may remember that the M over Z value is the mass over charge, and as we said that most of the ions are single plus charge ions. Therefore the M over Z value is just the mass number divided by 1, because most of the ions that hit the detector are single plus ions, so this will be 1. Therefore, the M over Z value really is showing the mass number of the particle or the species hitting the detector. Hence, the M over Z value of the molecular ion peak tells us the relative molecular mass of the molecule. This peak here is called a satellite peak. This is due to the existence of carbon-13 isotopes in the molecules. And this peak is quite small because the percentage of carbon-13 is a lot smaller than carbon-12. So a molecule with one of the carbon-12s replaced by carbon-13 will have an MR which is one bigger than the MR of the molecular ion peak. A molecule with two carbon-12s replaced by two carbon-13s will be possible, but that would be very rare and the peak will be very, very small. Using the empirical formula mass and the relative molecular mass from the M over Z value of the molecular ion peak, we can work out the actual molecular formula of the compound. The empirical formula mass for C2H5 is 29, and the relative molecular mass divided by the empirical formula mass is 2. So therefore the molecular formula is twice the size of the empirical formula, which gives us in this case C4H10 as the molecular formula. What we do then is draw all the possible structural isomers of C4H10 in this case, and then see which one of those structures can form fragment ions which will match the M over Z values of the fragment peaks. So therefore we can work out which of those structures this mass spectrum belongs to. So in the case of C4H10, there are two possible structural isomers that we can draw, and that's butane and 2-methyl propane. And what I've done here is drawn the display formula for both of these. I've shown how we can form fragments by breaking one bond along the molecule. So in the case of butane, I can form a methyl fragment, an ethyl fragment, a propyl fragment, and those are the only fragments I can form. And the M of Z values I've written here. 2-methyl propane, there's only two possible fragments I can form. If I break this bond here, it's the same as breaking this bond here because these two methyl groups are interchangeable. Looking back at the original mass spectrum, we can see that there are three prominent fragment peaks. I haven't drawn in, by the way, other fragment peaks which will appear. We don't normally interpret every single fragment peak, only the ones that are prominent or labelled in the exam. In this case, the fragment with M over Z value of 15 is likely to be a CH3 fragment. We must write the charge of the fragment ion in the exam, otherwise you won't get the marks. The other way of drawing fragment ions is through display formulae, so if you do display formulae, you must draw the brackets as well, and then put the plus sign on the outside. So you can also draw fragment ions as this. So there are different ways of drawing those fragment ions, but in every case you must put the plus sign on the fragment ions. A possible fragment ion that forms an M over Z value of 29 could be this fragment ion, which can be written as, you can write in skeletal as well, but not for this ion. The fragment peak with an M over Z value of 43 could be formed from this fragment ion, and we can draw these fragment ions using skeletal as well. So I've shown you different ways of drawing fragment ions, but try not to use molecular formula as we said before for organic chemistry, as the other ways of drawing formulae shows more structure, which is better. So this mass spectrum can only be formed by a molecule which can form fragment ions with M over Z values of 15, 29 and 43. And the molecular ion peak is 58, so it has an MR of 58. So if we look at the two possible structures we proposed earlier, the only one that matches the spectrum would be this one here, as butane can form those three fragment peaks, whereas the 2-methyl propane cannot form the fragment peak with MOZ value of 29. So I've concluded that it is unlikely the sample is 2-methyl propane, as this cannot form a fragment peak with M over Z value of 29. So here's another example of a mass spectrum, and we want to see whether this mass spectrum will fit two possible structures. So we have pentan-2-one, this is a ketone, and pentan-3-one, which is a structural isomer of pentan-2-one. They're both ketones. So what I've done here is drawn the structure of both of these molecules, and I've shown the break or cleavage of one bond along the molecule to form different fragment ions, and shown the M over Z values of each of those fragment ions. So for example, I've got a CH3 fragment here with an M over Z value of 15, and if I break or cleave this bond, I get a fragment of an M over Z of 43. If I break this bond or cleave that bond there, I have a fragment with an M over Z value of 57. So I've gone along the molecule to see what fragments I can make by breaking one bond, remembering not to break any double bonds. I've done it here as well for the pentan-3-one. and I've shown the MOZ values of those fragments through cleaving or breaking one bond. So cleaving this bond here, breaking that bond here, I get a fragment with an MOZ value of 29. The mass spectrum given to us has a molecular ion peak of 86. I haven't shown in this case the n+1 peak, but there would likely be an n+1 peak there. The MOZ of 86 matches both of these because these are structural isomers, so these both have MRs of 86. Now if I look at the prominent fragment peaks, I can see that there's a fragment peak with an MOZ value of 29. Now both these ketones can produce a fragment of 29, so this one here, we can see there's a fragment here of 29, which is an E-file. And this one here can also produce an E-file fragment. The other prominent fragment peak with an MOZ value of 57 still wouldn't be able to tell us which of these two compounds produce this spectrum, because both of these compounds can form a fragment ion of MOZ value of 57. So in the A-level exam, you're not expected to be able to tell which of these two compounds will form this spectrum. But these two compounds, interestingly, have different mass spectra and they look slightly different. So I've sketched them here. So the pentan 2-ion has this mass spectrum and the pentan 3-ion has this mass spectrum. And you can see that the prominent fragment ions are different for the two spectra, for the two different compounds. For A-level, you're not expected to work out which is which. So in the case of an A-level question, if they do ask you which of these two compounds form this spectrum, you just say that both of these can form that spectrum. You're not expected to be able to work out for the A-level which is the more likely one to form this spectrum. So we covered in this video that a molecular ion peak is the peak in the mass spectrum which is formed by the molecule being ionized by high energy electrons at the start of the process in the mass spectrometer. The n+1 peak in the mass spectrum is caused by carbon-13 isotopes, which is one of the stable isotopes of carbon. The carbon-13 n+1 peak is much smaller than the other peaks because carbon-13 is a lot less abundant than carbon-12. We then looked at how fragmentation occurs in the mass spectrometer and why we get fragment peaks, and those fragment peaks are due to fragment ions. And also we looked at the fact that different structural isomers can give us different fragment ions, and therefore by analysing the spectra we can work out what possible structures cause this spectra.